numerical integration for singular or unbounded cases. Unbounded cases. So we did the Newton codes, right? For if you recall, the Newton codes, which is you have an interval, right? You have interval. First of all, it's bounded. It's bounded. It's from A to B, and right? And we said, okay, we're going to take 3 points, for example, right? Or cut that into many smaller intervals, and on each interval, we're going to take 3 points, which in particular includes the 2 endpoints, right? 2 endpoints. 2 endpoints. And we're going to do a summation of what is it? Of I f at xi, right? I is from 0 to n. So the question is that what if f at for example x0, right, is infinity, plus minus infinity, or the domain is unbounded. This is covered in the book, and I'm going to give you 2 examples here, one for each. Okay. So one example is that if we want to integrate 0, 1 to 1 of 1 over square root of x, right? 1 over square root of x. Or maybe let's multiply by 2. All right, 1 over square root of x dx. This function, if you were to apply the Simpson's rule, for example, you would have to evaluate the function at 0, right? At 0, which is infinity, right? Which is infinity. So you cannot really do that. That's a singular case, right? It's singular. So the function is singular at 0, right? When you do your alpha 0 times f at x0, that wouldn't work, right? That wouldn't work. But this is a perfect fine function to integrate, as you might remember from calculus. This function is so-called integrable, even though it is singular at 0, but it's integrable because we know it's antiderivative. The antiderivative is square root of x, right? And we evaluate, we know it's 1. So it's perfectly integrable, right? So with this in mind, with this example in mind, it's a typical example, right? It's something perfectly integrable, and if you try to apply the numerical integration, you at least for the current ones, we cannot do it, right? One strategy, as we'll see later, right, is that you can find a quadratic rule which does not involve the 2 endpoints. Then you can actually do it. If I don't need to evaluate the point at 0, then we're fine, right? But let's leave that for later. For now, let's actually talk about a slightly more general case, which is if we want to integrate from 0 to b, right, a function, a phi of x divided by x to the mu dx. And I'm assuming mu is larger than or equal to 0 and less than 1. And less than 1, right? Less than 1. Then this can be perfectly integrable. So one idea is that is that we can examine the integral. We can split it into two parts. We can single out the trouble region, right? The sort of trouble region where it is close to the zero. From 0 to epsilon, some small epsilon, right? Phi x divided by x to the mu dx plus epsilon to b phi x divided by epsilon x to the mu dx, right? Dx. If phi is not equal to 1, this is not easy to integrate by hand, right? That example was just trivial because we know the exact antiderivative. Of course, we'll talk about a general function. What you may not know is exact antiderivative, right? So we always need to resort to some sort of numerical tools. So if we denote this by I1 and I2, right? So the I2 is the second part. So the I1 is from 0 to epsilon. I2 is from epsilon to b, right? This part is fine. This part is fine. Just do the regular. We can do the regular numerical integration, right? That is fine. Split that into using, for example, using the composite. What's that? Simpson's rule, right? Split that into many smaller intervals. On each interval, do Simpson's rule, which again has a weight over 6, 4 over 6, 4 over 6, right? You have a third set of homework, which is about these things. I1 is tricky. I1 is tricky. And as we were saying, as we're using often, right? So the epsilon is small. So a frequent tool that we use frequently is the Taylor expansion. Here again is Taylor expansion. When epsilon is small, we're talking about small neighborhood of 0, right? We can do this thing as the following. We can expand the phi of x to be I from 0 to k, right? And we're going to get a phi to the i's derivative of 0 divided by I factorial, and then x to the i's power, right? Plus 0 to epsilon. K plus 1. We're going to write this phi k plus 1 at some c between 0 and epsilon divided by k plus 1 factorial. All right, and then we're going to have this x to the k plus 1 divided by x to the mu dx, right? Dx. And what is this? This is the integral of a sum, so we can switch the order. You're going to get I from 0 to k, and the coefficients are constants. So we have phi i's derivative of 0 divided by I factorial, an integral of 0 to epsilon. X to the I divided by x to the mu, that's x to the I minus mu dx, right? Dx. So we're given a phi, we can evaluate its derivatives at 0, which we all know, right? For the second term, we don't know. We're going to denote that by some arrow, right? EI1. We're going to basically forget about it. We're going to treat 0. This is we're going to treat this as 0. We're going to approximate by 0, right? So we're making an error, which is that term, which we'll estimate later. Okay, so this we can compute because we know how to integrate it from 0 to k of phi I 0 I factorial, right? I factorial, and x to the I minus mu. This antiderivative is so because I is at least 0, right? And the mu, we are given the mu is larger than 0 and less than 1. So mu is less than 1, which means I minus mu is larger than negative 1, right? Otherwise you would have a log. So when it's larger than negative 1, its antiderivative is you raise it by 1, so it's I minus mu plus 1 divided by I minus mu plus 1, right? And this evaluate between 0 and epsilon. All right, 0 and epsilon, which of course we can compute, which is summation of I from 0 to k of phi I 0 divided by I factorial times epsilon to the epsilon to the I minus mu plus 1 divided by I minus mu plus 1, right? I minus mu plus 1. Okay, you plug in 0, get a 0. Right? This is a quantity you can compute by taking a small epsilon, by raising the k. You do 2 terms, 3 terms, 4 terms of Taylor series expansion. Include them. You're going to get a better approximation, right? So again, so if you're raising k, this will lead to better approximation of I1, right? Of I1. Okay, of I1. So the error. What is the error? The error, which is that term E I1 absolute value, which we can bound, right? Which we can bound, which is the maximum over for all the c, right? C between 0 and epsilon. Okay, your phi to the k plus 1 derivative of that c. Then once you are given a function phi, you can compute this. You can estimate this. It's upper bound. Is the largest possible value, right, between of the k plus 1 derivative of this function. So obviously, when for the example the phi is 1, then you get 0, right? You get 0. When phi is 1, we're going to get an exact. For different phi, as long as you can find upper bound of the k plus 1 derivative on that interval, right? Times what? It's x to the k plus 1 minus mu, right? We're integrating this guy. So the integral of this is less than, I take the absolute value of this integral is less than, I take the largest possible guy here. I put them out here, right? I integrate x to k plus 1 minus mu divided by k plus 1 factorial. So this is 1 over k plus 1 factorial. X to the k plus 1 minus mu becomes epsilon to the k plus 2 minus mu divided by k plus 2 minus mu, right? All right. So if we can bound the m as the k plus 1 derivative by some m, right? This is m times 1 over k plus 1 factorial, and then we have epsilon to the k plus 2 minus mu over k plus 2 minus mu. This can be very small if k is large and epsilon is small, right? Okay. So we're going to, it's a singular integral, but we're going to get as accurate as possible, right? And for the Simpsons, for the second part, the I2, we talked about the Simpsons rule already. We know this arrow. Okay, we have that. So two sources of arrow. We have some arrow for I1, some arrow for I2. We can quantify both. For the I2, we use the Simpsons rule, which we talked about already, the arrow. Okay. For example, right? If the phi is equal to cosine x, say we are integrating from 0 to 2 pi of cosine x divided by square root of x, and here mu is 1/2, right? Here mu is 1/2. Mu is 1/2. All right. Mu is 1/2. In this case, our phi is cosine x, our m is what? We can take m to be what? So we can take the m to be 1. So what we're saying here is the following, right? So if you want 6 digits, maybe I should have studied that. You want 6 digits accuracy, 10 to the negative 6 accuracy. All right. So our goal is to figure out, okay, how many intervals should we use, and so on and so forth. What is k, right? So which means error is less than 10 to negative 6, right? So the error again, the error is we have error from I1, we have error from I2. For you to make sure the total error is less than 10 to the negative 6, I want at least 6-digit accuracy, which means you can distribute them in the way you want, but maybe one way to split them. Okay, if I want this guy to have error is 10, 5, 10 to the negative 7, here 5, 10 to the negative 7. They add up to be 10 to the negative 6. Okay. So which means we should make sure that the error, right? The error, which is m is 1, so m times 1 over k plus 1 factorial times epsilon to the k plus 2 minus mu we know is 1/2 divided by k plus 2 minus 1/2. That's error when we're close to 0, a singular point. We want to make sure this is less than 5 times 10 to the negative 7. This is possible if we take, say, we're going to integrate 0 from 2 to 2 pi of cosine x over square root of x dx. We're going to take epsilon to the, 0.05, all right, plus 0.05 to 2 pi, which means the epsilon is equal to Yeah, 0.05. Right? That's our epsilon. So as long as we take a k that's large enough, we can make this happen. So which means we should take k large enough so that, again, m is 1. So it's 1 over k plus 1 factorial times epsilon, which is 0.05 to the k plus 2 minus 1 half divided by k plus 2 minus 1 half. This is less than 5 times 10 to negative 7. That's an error. We're not saying error is between 0 and 1. That's an error. So by taking this k, right, by taking this, any k that can serve this purpose. Of course, maybe you want to take the smallest k that serve this purpose. You stop there. Take that k, you take the derivative all the way to of cosine x all the way to k, right? You do that series, this guy. You do what is it? You do this guy, right? This guy. Once you fix the k, you have phi, which is cosine. You can compute that. We know epsilon, which is 0.05. We can compute that series, right? And the only part that we want to make sure is for the I2, right? So the I2 now is that we want to, again, quantify the error. This 0.05 to 2 pi of cosine x divided by square root of x dx. Okay? We use the composite Simpsons, for example. Right? We're going to divide this into many pieces, right? 0.05 to 2 pi. Divide that into many pieces. On each piece, we have, as we explained last week, right? On each piece, we'll do 3 points, right? And here again 3 points. So when we talk about the error, the error for the error committed by I2, right? This is less than, we know is bounded by less than or equal to what? That b minus a, right? So we have the b minus a which we know is 2 pi minus 0.05 divided by, I think it's 90 times 2 to the 5th. Okay. And h to the 4th. What is h? If you use n intervals, we know h, which is 2 pi minus 0.5 divided by n to the 4th. Okay. And the 4th derivative, which is, we have the cosine x divided by square root of x, this guy, to the 4th derivative at c. At some c, which you can bound. You can take the 4th derivative, you can bound, and which means that we take n. We use as many intervals as necessary. We take n large enough so that this quantity is also less than 5 times 10 to negative 7. Then we're done. At least we can get a start on the other part, which is what if we're integrating a function on an unbounded domain. For example, we want to integrate from a to infinity of f of x dx. of x dx. Right. Okay. So what would be a good example? It's the unbounded domain, but it's still integrable, right? So what would you say if you want to integrate from 1 to infinity of 1 over x? Can we integrate 1 over x? Is that integrable? Meaning, is the integral finite? Yes? The answer is no, right? It's log x, log infinity is infinity. So you need a power, any power that's larger than 1. Actually, 1 plus any tiny guy would make this integrable. That's interesting, but if we certainly don't need to take 2. But if we take 2, the integral, the antiderivative is -1 over x, right? Between 1 and infinity, we're going to get 1. So again, this function is perfectly integrable. The integral is 1. But if we were to apply the rules we have right now, again, there are other quadrature rules that will help us. Okay, but if we do it using the ways we currently have, we're stuck, right? And again, but similarly to the singular case we just did, with the tools that can help us. Okay, so again, we try to split that into 2 parts. One is that we're going to do from a to some constant c of our f of x dx, plus then from c to infinity of our f of x dx, right? We're going to take care of the first part by doing the regular integration, say the composite Simpsons, for example. For the second part, we need to do something with it, to do something about it. Okay? Do something about it. And what do you think? What is so for this guy, for f of x dx to be finite, right? For this function to be integrable, f of x should go to what? As x go to infinity? 0, right? 0, 0, 0, 0. As a simple lemma from calculus. Otherwise, this is not integrable. Okay. In fact, as we just talked about, we cannot really integrate 1 over x. 1 over x goes to 0 as x goes to infinity. So it's actually something stronger than just going to 0. In fact, the f of x should go to 0 faster than 1 over x going to 0. Which again means that if we multiply x to the 1 plus rho times f of x, this actually go to 0 for some rho, for some positive rho. So this is what I just said. When we integrate, we cannot integrate 1 over x, but we can integrate 1 over x to the 1.1 or 1.01, as long as the power is larger than 1. So f of x should more or less like 1 over x to 1 plus rho for tiny rho. Okay, for tiny rho.